I had a strange distinction, or actually many of us, and you'll see a full list, had a strange distinction of serving on the last committee with Stuart, or the last committee that Stuart ever served on. Maybe unfortunate distinction. We'll talk actually about the outcomes of our review of various ways the neutrino mass hierarchy can be measured. That was the goal of our study. I will start though with obviously my personal connections to Stuart. I'm younger than most here. I venture to say. So I first met Stuart in '98. I actually also am ashamed to say this thing was a blur. I was in this prize session at the DNP meeting. I was given the last talk, and there were clearly luminaries in the audience before me. I was a little awestruck. Here's Dick Waleczka, Betsy Bees, John Bacall. I'm not sure I actually knew who Stuart was. He was on the stage. He was the chair of DNP, so he presented me with this prize. He looked as young as ever. I looked as young as I do now. This was my first meeting, and actually Stuart made a point later on. Whenever he would introduce me to somebody new, he would say, "Oh yeah, and I met him at the APS meeting." And so I was kind of proud to have that connection. And then I didn't realize that, in fact, my connection to Stuart, in fact, or at least our family connection to Stuart goes back probably 20 years or so. And I only realized that recently there's actually a paper from, well, the paper's from 2000, but it's this NPD gamma experiment that, as far as I understand, has been running for 20 years. So it actually has my family name there. That's my uncle in the St. Petersburg Nuclear Physics Institute, who's been doing neutron physics for all of his adult life. And here's Stuart, and of course, unfortunately, my uncle doesn't know how to spell family name. This was, in fact, they did collaborate. I asked my uncle about Stuart. He actually remembered, had nice words to say, although he generally in Russia at the time, there was some healthy disdain for Yankees. But of course, nobody in the right mind would call Stuart a Yank, so, there was mutual respect, and I think Stuart actually remembered the name from somewhere. This was the connection before I came to Berkeley. So I arrived here in 2001, and the university very promptly started working on my green card case. That was very good of them. And so I asked Stuart. So they told me that I need to apply through this outstanding professor researcher category that requires at least an inch of paperwork. They actually told me you have to have at least an inch of papers collected. They measured it with a ruler. And among those, that stack of papers, there had to be letters of recommendation for this green card case. And they told me I have to go and ask luminaries in the field, and Nobel Prize laureates would be nice. I didn't know many Nobel Prize laureates at the time. So I went to the closest luminary that I knew, which was Stuart. And Stuart was very nice. He said, again, our connection at the time was somewhat tenuous, but he agreed immediately to write me a letter. He wrote a great letter. One thing about these green card cases, and people who went through this know that this is probably the only time in your adult professional life where you actually get to read your own letters. And you have to forget them right away, because otherwise they get to your head and you sort of, think too highly of yourself. So I read Stuart's letter. It was great. I had to promptly forget what I read, except for one sentence there. And this sentence there sticks to me to this day. In fact, I may have to steal it for cases that I write for people. He finished this letter with this phrase. That just blew me away. It should have blown the INS away. It didn't quite. I got my green card in 2008. I know. So Stuart does have a pool, but not as much in the INS, perhaps. But this was just awesome, and I was actually very touched. I worked at the time on two experiments, Babar at SLAC, and the fixed target experiment called Even 58 that measured parity violation, so I had my hands full. But towards 2003, when 58 was already running, so I was looking for some new challenges. And of course, it was impossible to escape Stuart's gravitational pull at the time. Either I was walking by his office or he dropped me an email. So he pulled me into this project called Diablo Canyon, which was a great fun at the time. It, at some point, transformed into Diabay. Most of you know the story of that. So when Stuart became persona non grata in China, I decided that there are better things to do as well. So at the time, Stuart also started working on CUORE, and it was very natural for us to continue the collaboration. So again, I couldn't escape Stuart's personality at that point as well. And Frank yesterday said that Stuart sold Frank on Gran Sasso, on the virtues of Gran Sasso, saying that it's a great place to live, it has beautiful women, great wine. I'm not sure about women. Well, at least Stuart didn't tell me about women. He told me about horizontal access to the lab space. But of course, great food, great wine, that came up in the conversation repeatedly. So, many an evening was spent on the deck of Hotel Nido dell'Aquila up in the hills above Gran Sasso, above the lab, drinking one of the great local wines, either Marina Cvetic or Testarossa. So in fact, this has to do with beautiful women, right? So, every great wine has to be named after one. So we had a great time, and I still remember this fondly. Richard was there as well. But of course, the main reason to go to Gran Sasso is not beautiful women or great wine, but to actually answer the greatest mysteries in the universe. And here's one. This is probably the greatest mystery in the universe that we had to repeatedly experimentally test, which is, do you get the clear or brown grappa? And those of you who tasted grappa know that there's a great hierarchy of scale in this local product. Most of the time it tastes awful. It tastes like cleaning fluid, but every once in a while you get some great product that you can enjoy. I actually found a picture that I think I took on the last trip Stuart and I took to Gran Sasso of some grappa that we found in the bar in Nido dell'Aquila Hotel. So it must be good. There must be a reason to take this picture. Although the name here is, it says morbid, so I'm not sure. But somehow this probably the greatest mystery in the universe eventually got answered. Stuart, so again, every speaker yesterday very fondly remembered how Stuart would tease them, and that's actually a sign that he respected you a lot. So one has to understand and appreciate that, and he, of course, had to find something to tease me about. And so he developed this Freedman Conservation Law that he would repeatedly tell me. Everybody, again, knows that he had a healthy disdain for bureaucracy. And in fact, he always would blame me personally for the increase in the amount of bureaucracy that seems to occur in the United States. And the story goes as follows. He said, well, of course, there's a conservation law. The amount of bureaucratic BS in the universe is conserved. And of course, everybody knows Soviet Union had a lot of bureaucratic BS. So when the wall came down and you came here, that stuff had to follow. So that was his argument, and my argument was that in fact it works like the third law of thermodynamics. So that absolves my responsibility. In fact, the amount of bureaucratic BS in the modern Russia is no less than it was in the Soviet Union. So this was another law that was developed, and of course he liked to point that out. That was his teasing of me, and of course, again, like all of us, had a lot of opportunities to discuss that and other issues of international collaborations, both in Italy and in the US, walking by his office and him calling out my name. And then he would sit down and say, Yuri, so what do I have to do now? Perhaps discussing interactions with Oliviero and company, or maybe some other aspects of doing science in larger collaborations. So as I mentioned, this was perhaps the last bureaucratic activity, or maybe scientific/bureaucratic activity we had to undertake. The two divisions at LBL in 2012 appointed this committee that Gabriel here and I chaired, and we invited luminaries in neutrino physics to work with us. So Stuart was one of them. In fact, in our report that Bob wrote a beautiful dedication in the front page of the report, saying that, I will have to paraphrase, that we obviously had very high standards to uphold, with this report in particular, very high standards that would make Stuart proud. So we tried. The object of the study was to look at the experimental ways the neutrino mass hierarchy could be determined in the next 10 or 15 years. Obviously, having in mind that the previous studies like this at LBL have actually resulted in great success. And Bob has mentioned yesterday the fact that a similar neutrino study in the late 1990s resulted in half of the committee joining Camland. So we had hopes that something similar would be developed. And again, this type of look serves both internal and external purposes. This is in some sense the role of a national lab to critically look at the difficult problems facing the field and try to suggest or come up with creative solutions. And as clearly LBL had a lot to say in the development of some of the experiments that are shown here, Snow, Camland, and Diabay, that came out from similar studies, similar investigations of what is the next challenging, important question to answer in the field. So we looked at the question of how one does experimentally determine the neutrino mass hierarchy, that is the ordering of neutrino mass states that we currently list as either normal, where the first electron-like neutrino state is lightest, versus the inverted hierarchy, where the electron-like state is heavier, and then the tau-like state. And of course, this question has important implications. It has important implications for the double beta decay field, in which we are very actively involved, but also other questions in fundamental questions in physics. For example, the mass scale itself has potential sensitivity to the grand unified scales. So answering these questions in the next 10 years would be important and would actually stimulate further development in neutrino physics and perhaps elsewhere in cosmology as well. So if we look at how which processes can be sensitive to the question of neutrino mass hierarchy, there are several of these. In particular, one can look at this side or this side. For example, there are some measurements that are sensitive to the neutrino mass hierarchy, but may not necessarily determine it directly. Neutrinoless double beta decay sensitivity clearly depends on whether the ordering of the neutrino mass states is normal or inverted, but unless we actually discover double beta decay process in the next 5 or 10 years, it wouldn't necessarily answer the question of the hierarchy itself. So we focused on the more direct ways to measure the mass ordering, in particular the long baseline oscillation experiments, reactor experiments, atmospheric neutrinos, and cosmology. And so I did mention the fact that the sensitivity of neutrinoless double beta decay depends directly on this question of the ordering. If one looks at the effective Majorana mass that's measured in neutrinos double beta decay, at least in the neutrino mixing interpretation of neutrinos double beta decay, the sensitivity, the lifetime depends quadratically on this effective neutrino mass squared. That is a linear combination of various three light neutrino states. And this linear combination can be either relatively high and in the range of the experiments that are currently being built, accessible range, or it can be of the order of few electron volts and therefore would be significantly more challenging to study directly neutrinos double beta decay, at least in the near future. So this question has quite a bit of relevance for our current program. Of course, one way to study this directly is to look at the neutrino oscillations over long baselines and take advantage of the meta-enhanced oscillations. And there are two experiments that are currently running that have relatively long baselines, a 200 kilometer or so baseline in T2K that's too short to determine the hierarchy directly, but combined with NOVA has actually sensitivity due to the fact that one of these experiments can measure a CP phase, that's T2K, and then combination of NOVA and T2K can actually determine if the conditions are right, with some about 50% probability, the mass ordering. So we looked at how T2K and NOVA can be sensitive. And so there is actually a decent chance, especially if the experiment is lucky, given a particular choice of the CP violation parameter, that they may have an indication of the hierarchy at the 2 to 3 sigma level. Of course, the major part of the US program is LBNE. It's one of the flagship programs that's being proposed for Fermilab, or to be centered at Fermilab. It's also one of the flagship programs that's being discussed now in P5 and was discussed at SNOMAS. The main goal of LBNE is to look at very precisely at neutrino oscillations over the distance scales of about 1,000 kilometers, and which is large enough to be able to disentangle independently the effects of CP violation and the effects of the MSW meta-enhanced neutrino oscillations. This sensitivity of LBNE depends somewhat on the mass scale, depends somewhat less on whether it's on the ground or not. So we looked at the standard set of parameters, which is the 10 kiloton detector on the surface, which is what has been approved so far. And even in this case, almost independently of the delta CP, the experiment should be able to determine the ordering of the masses to about 3 sigma or more. Of course, there's still open questions, and we actually, the combination of the physics division and nuclear science division was actually fairly well positioned to ask some of these difficult questions, in particular effects of the nuclear physics in the relatively heavy targets in liquid argon that may potentially spoil the measurement or introduce systematics that needs to be understood. And of course, questions of timescale and cost will be in LBNE will have to be addressed by the community very seriously as we are planning for our future. So we did want to look also at alternatives, in particular the long baseline measurements elsewhere, and Hyperk, in fact, is one of the experiments that is very high on the priority list in Japan. It's a megaton Walter-Cherenkov detector at a relatively short baselines, and so therefore its sensitivity to meta-enhanced oscillations is limited. However, a combination of atmospheric neutrino measurements and long baseline measurements can potentially resolve the hierarchy at about 3 sigma level. And so in that sense, this experiment is quite complementary to LBNE, especially since it uses a different detection technique. It's a Walter-Cherenkov as opposed to liquid argon detector. And there are also a couple of experiments that were very tantalizing to us, and the committee stimulated a lot of very lively discussions. One of them is a spin-off of a diabase, very highly successful diabase experiment that used to be called diabase 2. Now it's called JUNO, since the experiment is no longer in diabase, but about a few hundred kilometers kind of southwest, I suppose. It's a major project in China. It's a very large 20 kiloton liquid scintillator detector. So it's, by comparison, this is the current size of SNO, SNO Plus, which is about a kiloton. JUNO is 20 times larger. So this presents both technological, technical, and physics challenges. The experiment relies on a very precise measurement of subleading oscillations as a function of energy, and therefore requires exquisite energy resolution, very good position resolution, requires excellent light collection. So it requires about 4 factors of 2 improvements in technology compared to the current state of the art. So it's an extremely challenging experiment. We want to understand whether the proponents did due diligence analyzing the systematics. We also wanted to understand the technology, whether technology is viable. So on paper, this is an experiment that over the time scale of about 5 years can actually determine the hierarchy to about 3 to 4 sigma, depending on the assumptions about the delta M to 3. But is extremely technically challenging, but perhaps exciting. That makes the experiment potentially exciting as well. Difficult experiment. So the other perhaps dark horse at the time was the neutrino, atmospheric neutrino measurement in the Antarctic ice. This is the experiment called PINGU, which is a spin-off of IceCube and Deep Core, the currently running experiments. So PINGU proposes to deploy a set of strings similar to IceCube strings, very closely spaced in the center of the currently deployed IceCube detector. That would lower the energy threshold of the experiment significantly, a few GeV, and allow one to look at the low energy side of the atmospheric neutrino spectrum, where one can then resolve the energy-dependent oscillation pattern. And that energy-dependent oscillation pattern depends on the ordering of the neutrino mass hierarchy due to the same MSW effect, matter-enhanced oscillations in the Earth's crust as the atmospheric neutrinos propagate from the other side of the Earth. So we had to understand, there was some analysis in the literature that claimed a relatively low significance, different from what the proponents claim. We wanted to understand that. So there are some differences that I think are now a little bit better understood. We wanted to look at the issues of energy resolution and scale and how they would impact the ultimate sensitivity of the experiment. In particular, how one would potentially calibrate this experiment. And so this is actually an example of an experiment that's relatively small scale, where a national lab like OBL can play significant role. In fact, there has already been some interest locally in joining and improving and actually leading this measurement. And of course, OBL is also very active in cosmology. We have a very healthy cosmology group that's spun off primarily from particle physics in the physics division. And of course, cosmological fits now can be viewed as a precise neutrino experiments. Cosmological fits, and from the large area surveys, such as Big Boss in the future, or LSST, will be sensitive to the total sum of the light neutrino masses. And therefore, depending on the answer those cosmological fits return, may be sensitive to the neutrino mass hierarchy. If the sum of the neutrino masses is measured to be relatively large, we would determine that neutrino mass hierarchy would have to be inverted, and vice versa. Of course, if the sum of the neutrino masses is determined to be small, we wouldn't be able to tell necessarily the ordering. But over the next 10 to 15 years, when the precision cosmology really starts to reach tens of electron volts in the sensitivity to the neutrino mass scale, this, so somewhere on the time scale of 2025 to 2030, cosmology may actually probe this question directly. And of course, being experimentalists and being primarily terrestrial experiments, or terrestrial experimentalists, we would want to check the answer from cosmology locally. So it's very important to have a complementary program, both looking at the heavens and doing the experiments here on the ground. And of course, perhaps in the best scenario, one will actually see a discrepancy between the cosmologically determined hierarchy and hierarchy determined here on Earth that may possibly tell us about something completely new and unexpected. Maybe it'll tell us something about cosmology, or maybe it'll tell us something about the nature of neutrinos. So this would be perhaps the best of possible worlds. But cosmological constraints, of course, play an important role. So at the end of our study, we put together this cartoon of how the different experiments would be sensitive to the neutrino mass hierarchy and what timescales, both from including cosmology long baseline experiments, reactor-based experiments, near-term oscillation experiments, and atmospheric PINGU. There's a big range here, depending on whether one believes the proponents of the experiment or an independent but somewhat pessimistic verification of the sensitivity. Of course, there's also a great complementarity in the techniques. And so if several of these measurements go ahead, one can potentially improve the sensitivity by combining the information. So for example, combining no and T2K is one example of that, but obviously combining the short baseline and long baseline experiments, or combining reactor and atmospheric experiments is another example of this. So there's clearly an interesting and an important future in this field, and possibly exciting future in this field, and we look forward to seeing these experiments completed and actually having LBL play an important role in this experiment, in these measurements. Of course, we had to, as I mentioned, this was the committee that had Stuart on as active participants in our discussions. In the beginning, we had to finish this report without Stuart. Unfortunately, it's clearly was a great loss, both to the community and to us. It remains to be seen whether what we've done is up to Stuart's high standards. But I think that really the question of neutrino hierarchy has been answered long before. And this obviously requires no explanation. And so just to close, I've read my green card case relatively recently for some strange reason. I again saw Stuart's letter, and that struck me. I've been privileged to work with Stuart. We were neighbors next to, well, at least on the third floor of LeConte, but I really would have loved to have him as my neighbor, and I miss him. Thank you.